Section 1. Building the Universe. An Introduction to Structural Engineering and Statics. Written by Neil deGrasse Tyson. Imagine gazing up at a skyscraper, a majestic bridge, or a magnificent dam. These awe-inspiring structures are testaments to the power of engineering, specifically a branch known as structural engineering. Structural engineering is the art and science of designing and analyzing structures that can withstand the relentless forces of nature and the demands of human use. At the heart of structural engineering lies a fundamental principle: statics. Statics is the study of forces and their effects on bodies at rest. It's like a cosmic balancing act, where structures remain stable and secure because the forces acting upon them are in perfect equilibrium. Just as the planets maintain their orbits due to a delicate balance of gravitational forces, buildings and bridges stand firm because of the principles of statics. Statics provides the essential tools and knowledge to ensure that structures are safe, durable, and capable of withstanding the test of time. By understanding the principles of statics, engineers can predict how forces will impact a structure, calculate the stresses and strains within its materials, and design it to withstand these forces with strength to spare. From the smallest homes to the tallest skyscrapers, every structure we encounter in our daily lives owes its existence to the fundamental principles of statics. It's a testament to the power of human ingenuity, using the laws of physics to shape our world and create structures that inspire awe and wonder. Section 2. The Balancing Act, Understanding Static Equilibrium. Imagine a book resting peacefully on a table. It's not moving, it's not rotating, it's in a state of perfect balance. This, my friends, is static equilibrium. In the vast universe of physics, equilibrium signifies a state of balance, a cosmic harmony where opposing forces cancel each other out. For a structure to achieve static equilibrium, it must satisfy two crucial conditions. First, the sum of all forces acting on the structure must be zero. This means that every push, every pull, every force trying to move the structure in one direction must be counteracted by an equal and opposite force. Think of it as a cosmic tug-of-war, where both sides are perfectly matched, resulting in a stalemate. Second, the sum of all moments acting on the structure must also be zero. A moment, in simpler terms, is the tendency of a force to cause rotation. Imagine trying to open a door. The force you apply creates a moment around the hinges, causing the door to rotate. For a structure to be in equilibrium, every twisting, turning force must be balanced by an opposing moment. Static equilibrium is the bedrock of structural stability. By ensuring that structures are in equilibrium, engineers guarantee that they can withstand loads and forces without collapsing or toppling over. It's this elegant balance of forces that allows us to walk across bridges, work in skyscrapers, and live in homes without fear of them crumbling beneath us. Section 3. The Force of Nature, Defining Force and its Properties. Force is an omnipresent entity in our universe, a fundamental concept that governs the motion of planets, the flow of rivers, and yes, even the stability of buildings. In the realm of physics, force is any interaction that, when unopposed, will change the motion of an object. It's what makes objects move, stop, or change direction. We can characterize a force by its magnitude, direction, and point of application. Magnitude, simply put, is the strength or intensity of the force, how hard it pushes or pulls. Direction tells us where the force is acting, whether it's upwards, downwards, or sideways, and the point of application pinpoints the exact location where the force is applied to an object. To measure force, we use a unit called the Newton, named after the legendary Sir Isaac Newton. 1 Newton represents the force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. It's a universal language for quantifying the strength of pushes and pulls, allowing engineers to precisely calculate the forces acting on structures. Understanding force is crucial in structural engineering because it's the foundation for analyzing how structures behave under various loads. By quantifying forces, engineers can design structures that can withstand the constant push and pull of gravity, wind, and other external factors, ensuring their stability and longevity. Section 4. Joining forces, vector addition and resolution. Forces like cosmic dancers interact and combine to create a net effect on structures. Understanding how forces add and resolve is crucial for determining the overall stability of any structure. Thankfully, we have a powerful tool at our disposal: vectors. A vector is a mathematical representation of a force, characterized by its magnitude and direction. We depict vectors as arrows, with the length of the arrow representing the magnitude and the arrowhead pointing in the direction of the force. Vector addition allows us to combine multiple forces acting on a point. It's like adding arrows tip to tail, with the resulting arrow called the resultant, representing the combined effect of all the forces. Vector resolution is the opposite of addition. It involves breaking down a single force into its horizontal and vertical components. Imagine a force acting diagonally on a block. We can resolve this force into two perpendicular components, one pushing horizontally and the other pushing vertically. Vector addition and resolution are indispensable tools for structural engineers. By understanding how to combine and break down forces, engineers can analyze complex force systems and determine the net effect of multiple forces acting on a structure. It's like deciphering a cosmic dance of forces, understanding how they interact to influence the overall stability of buildings, bridges, and everything in between.